Hi, I'm Stu from HiveMind Automation and welcome to the Hive. In a previous video, I unboxed and reviewed the Mirabella Genio RGB and Cool White LED strip. In this video, we're going to look at making our own custom LED strips with a NodeMCU and this strip of addressable LEDs. We'll flash the NodeMCU with some custom firmware that uses MQTT to control the LED strip, and we'll integrate it with Home Assistant. So let's get started. Now, we took a look at the NodeMCU control board in a previous video. So let's take a closer look at this LED strip. I picked up two of these 5-meter strips from AliExpress for around $40 each, plus shipping, about 2 years ago. They have a density of 60 LEDs per meter, and you can get these strips in either higher or lower densities. This particular strip utilizes SK6812 modules, meaning they have red, green, blue, and white channels. These are sometimes also referred to as NeoPixels. And if we look closely at the LED module, you might see this two-tone effect on the lens, where half of the LED module has this yellow look and the other half has this silvery look. The yellow half is the white LED output, and the silver half over here is the RGB side. When you are purchasing these strips, you do need to choose whether you want cool white, warm white, or this is a neutral white version. So it should be somewhere in the middle, which is a kind of a coolish white that's not too blue and it's not too orange. You can also get flexible strips that utilize the WS2812 LED module, which is the same as is on this PCB module that I have right here. The difference with the WS2812 is that the 2812 doesn't include the white channel and it only has red, green, and blue. While theoretically setting all three RGB channels to 100%, it should produce white light. They do tend to skew very heavily to the blue channel, but you could potentially start adjusting that to color correct if you wanted to go down that path. I explicitly chose the 6812s because I wanted a separate white channel. Now, if we look closely at the contacts on this strip, you'll notice that there's only 3 contacts on these strips. There's a plus 5 volts, a D in, a ground, and over on this side you might see there's DO on the other side of the LED. And this is where the cleverness of the 6812s or the 2812 modules comes into play. Each of the LEDs on this strip is addressable individually. And that means that we can have effects lighting where different LEDs are either different colors or even some that are on, some that are off, and different brightnesses across the length of the strip. And that all happens down just a single digital signal wire, which is daisy chained on the input to the output and then to the input of the next one, and so on and so forth down to each LED in the queue. I also have these 24 LED rings on a PCB, and they're exactly the same 6812 modules, but they're on the PCB instead of a flexible strip. And this is the same as the LED strip I demonstrated in my MQTT video, and you can see on the back here that we have the same pins. We've got a power in, ground, and 5 volts DC. We've got data in, and there's also a data out pin that you can see here. So we could daisy chain multiple modules by then going to the data input on this module here from the data output on this module, and then keep going down the line. Similarly, this WS2812 module is exactly the same. If we take a look at the back, we have a VCC for 5 volts, we have a ground, we have in, and we have out. And with this particular one, because we've got the 3 different tiers, we would go from out to here to DI or digital in here, or vice versa. We could go from the outside in or the inside out. So one of the other things we'll note here is that this LED strip has a break in between each LED. So if we wanted to, we could actually just have this single LED module here and wire up to this and have a single LED in our array, or we could wire up to this and then have some cables coming out of the other side to another LED that's mounted further away. So these strips with the individual addressability are very flexible indeed for lighting projects. So we've got our NodeMCU and we've got our LED strip, and now we need to connect the two. Now, I've had a bunch of these around my house running LED lighting for various situations. Some time ago, I designed a custom PCB using the Easy EDA software on my Mac. And I had a bunch manufactured by JLC PCB. This board is pretty simple, and because of its simplicity, it also has a couple of serious limitations. It has mounting headers to receive the NodeMCU, a power plug to receive a standard 2.1mm power jack, a capacitor for some power smoothing. We've got a MOSFET here to switch the power rail to the LED strip on and off. And this could also be achieved by using a relay, but it would complicate the board design a little bit. And lastly on here, we have a 3-pin screw terminal block to connect the LED strip. A couple of the key limitations here are that I did hardwire the MOSFET gate pin and the LED strip digital out pin. So there's no flexibility in the way we code the software on the NodeMCU. Those pins have to be the ones that we connect the FET gate and the LED strip to. I also didn't add in a logic level shifter to ensure that we're pushing the digital pins at the right voltage. Now, in the case with the NodeMCU, this shouldn't be too much of a problem because most of the driving is done at 3.3 volts. However, I have heard that the SK6812 drive should probably be above about 4 volts. The last limitation of this board is that it doesn't have provision to work with LED strips that have a voltage other than 5 volts. And that's fine for my SK6812 strips, but there are some WS2812 strips that take 12 volts, and applying that much voltage to the input of the NodeMCU is a surefire way to cook it. I have been working on version 2 of this board with the provision for the logic shifter and selectable pins for the MOSFET and the digital output pins, but I haven't quite tackled the input voltage issue yet, and I might just end up adding a buck converter to version 2 of the board. So that's really enough about the hardware. Let's take a look at the software. Now, it's worth mentioning that I did find this whole project through another YouTube channel, Bra Automation, who demonstrated this setup using the WS2812 LED strips. Of course, I decided stupidly that I wanted to purchase the SK6812s because I wanted the separate white channel, which did cause a challenge with regard to the code shared on Bra Automation's GitHub. Thankfully, after some searching, I found a GitHub fork of the original code from .NET Dan, who modified the code to work with the SK6812s. Now, in preparation for this video, I did have some trouble with my setup of SK6812 LEDs and the latest version of this script. So I'll put a link to .NET Dan's GitHub repo, but I'll also fork the GitHub repo and upload my working version in there. And we'll have a link to that Bright Automations video and Bright Automations code, all in the video description down below. There is definitely a better project than this one, but it is worth talking about this before we explore the other one. So after downloading the code from GitHub, you'll have a whole bunch of stuff inside the extracted zip file, things like wiring diagrams, and this wiring diagram is exactly what I based my custom PCB off, except I did omit the resistors here and the logic level shifter. So if we were to take a look inside this reference folder, we'll actually see that we've got references for the SK6812 LED strips. We've got some data sheets for the P-channel MOSFET and some other bits and pieces in here as well. The most important folder in here is this ESP MQTT digital LEDs folder. And if I open that and then open up this ESP MQTT digital LEDs.ino file, I'll open that in the Arduino IDE, and we've got that, and it's also opened the other files in the folder. Now the main INO file tells us our dependencies in the comments section right at the top. So to use this code, we need the following dependencies: support for ESP8266 boards, and we discussed that in the ESP8266 video, or the NodeMCU video, and you can download the dependencies by going to the board manager and searching ESP8266 and installing it. We also need to download the following libraries by going to Sketch, Include Libraries, and Manage Libraries. We need the Adafruit NeoPixel, the PubSub client, and Arduino JSON. Something I discovered while trying to compile this code was if we go to Sketch and then Include Library, Manage Libraries, the Arduino JSON library that we need is actually anything in version 5. We can't use version 6 because version 6 breaks some syntax. We could potentially recode the code for version 6, but it's just easier to get going by using the correct version. So I'll also install the NeoPixel library, Adafruit NeoPixel, and PubSub client. So PubSub client is for MQTT, so we'll install that as well. Now we've got our main file that tells us a little bit about what's going on. We generally don't need to modify that. We have this section here which tells us all config in auth.h, but by default you will only have auth template.h, which tells us right at the top, add your keys and rename this file to auth.h. So I've already created an auth.h file, and I've entered my credentials for the Wi-Fi, I've entered my credentials for my MQTT server and the address for the MQTT server. And these are things that are problematic in terms of hard coding these into the code. I don't like hard coding anything, especially when it's credentials like our Wi-Fi, SSID and password. But we'll explore a better project in a future video. We've also got our details for our MQTT server, including a username and password. Again, problematic hard coding these passwords in here. We can define our data pin for our LEDs, which is currently on D8 in this code on the output of the NodeMCU. And we've also defined our relay pin, which is the same as our pin for the MOSFET on the board, to D7. So GPIO 13 or GPIO 15 corresponds to D8 and D7 on the ESP8266. We defined a maximum LED count of 300. We're also defining a default number of LEDs if there's no config set, and that we're setting that to 240. I don't know why that's so high. I might just change that to 24. We've also created a default device name of LED. And we're also using a maximum brightness of 255. We can change that if we wanted to 127, so that the LEDs will only ever come on to half brightness, and that can help with current limiting if you're having some issues with power supply. I'll leave that at 255 because we're not going to be driving a lot of LEDs in this particular case. We then go on to our setup configuration function, and straight away we've got some stuff going on. So we're outputting some data to the serial monitor. So we're printing a string of ESP chip ID, and then we want to actually print the actual chip ID. And that chip ID is handy because then what we do is we go, if the chip ID equals this, we want to call it this, and we want to change the LED count to this. We want to change the maximum brightness to this. So what you could do if you had multiple ESP8266s with this project is we could copy this block of code and we could paste that in here. We could change this ESP chip ID to whatever it is. So I'll put 1, 2, 3, 4, 5, 6, and we could call this kitchen island. Call that kitchen island. We could change the number of LEDs to 128, and we could change the maximum brightness, say, to 175, just to limit the current from the power supply. So what I'm going to do is save this. We've also got some things like our NeoPixel effects in here. We won't worry too much about that, and we've also got our web.h in here, and we won't worry too much about that. Really, the only thing that we need to worry about is this auth file here. So now that I've done that, I have plugged my ESP8266, or my NodeMCU, sorry, into the board, and you can see that over here. And I've also plugged in the micro USB cable so that we can program it. So I'm just going to click upload. And we're going to let the sketch upload to the NodeMCU. So it's resetting the NodeMCU, and now if I go to Tools and then Serial Monitor, what I should be able to do is reset the NodeMCU. Fantastic, and we see that it has the chip ID of that, and when we looked at the auth file, that is 5658691. 5658691, and then when we had that ESP chip ID, we wanted to give it the device name test, and it has 24 LEDs, maximum brightness of 255. Now what I actually want to do is modify this, because the LED strip that I have attached to this particular NodeMCU only has 23 LEDs, but it's not a big deal if we drive more than one. But what I'm going to do is just change that to 23 so that we have the correct number in our code, and I'll change that and upload again. Okay, great. So we've uploaded that again to the NodeMCU. Now what I'm going to do is unplug the NodeMCU from the USB port. I'm going to take my 5 volt 6 amp power supply here, which I purpose bought for these LED strips, and I'm going to plug it in to here. What we should see is the LEDs have come on, and in a second the first one went green and then it's turned off, and that is the boot sequence for that. It goes green to tell you that everything is good. So it's connected to Wi-Fi because we had those credentials in there. It's connected to MQTT. And so now if we go over to our Home Assistant, I'm going to take at the Visual Studio Code plugin here, and I'm going to take a quick look at this LED ring.yaml file, which we set up in our MQTT demonstration video. Now, if you watched that MQTT demonstration video, you'll remember that we set up the platform of MQTT. We gave it a name of LED ring. The schema was JSON. Our state topic was LED test, and the command topic is LED test set. We've enabled an effects list, and these are the list of the effects that are available. We enabled the brightness slider. We enabled the RGB selector, and we enabled the white value. We set our optimistic value to false and our quality of service to 0. This LED ring YAML file is being called in the configuration.yaml file. If I collapse some of this stuff, we should see we've got light and then bang include LED ring.yaml. So if we go back to our overview in here now, we'll scroll down to the light section here and we see we've got LED ring. And if I click on the icon next to it, we get the details of the LED ring and we can turn it on. And you'll see that it has turned on. I might bring the brightness there down to, and so that's just the white LEDs. We can bring the white value down a bit too. And that's just white. And we've got red, blue, and green. And then the other thing that we've got here is this effect section. So we've got solid, and we've also got clear, which just turns everything off. We also have this twinkle setting, and what happens with that is it twinkles in the color of your selection. So if I change that to purple, we get that. Change that to a blue, which is great. We've also then got Cylon bounce, which is kind of a nice effect, and that is just bouncing from one end of the LED strip to the other with the color selected. So if we wanted a proper Cylon, we could go for red. This fire effect is more of a projection effect. If you were to have this LED strip up against a white wall, it would kind of almost look like flames dancing on the wall. There's a fade in and out, which slowly fades in and out, as the name suggests. A strobe, which is probably not good if you are sensitive to light effects. A theater chase, which is quite nice. It just chases along the length of the strip. One of our favorites is rainbow cycle, which, as you can see across the length of the strip, it cycles through the colors of the rainbow. And that's a really nice effect to kind of show the flexibility of these individually addressable strips. You can have different colors on different LEDs. There's a color wipe as well, which if you choose a different color, it wipes that color from one end of the strip to the other. Running lights is another one that really demonstrates the individual addressability of the LEDs, where you have some on and some off, and they scroll along the length of the LED strip. Snow sparkle is one that just does a full color and then it flashes white LEDs through there as well. Sparkle just sparkles with the selected color. Twinkle random is it randomizes the color and it just kind of twinkles away there. And lightning is another favorite. It flashes segments of the LED strip at different intervals, and it's almost as if you're in the middle of a lightning storm, and I love that effect. And we can change the color of the lightning that is on there. Again, not great if you have any kind of flashing light sensitivity there, so use these at your own risk. So we'll take that back to, actually let's go to fade in and out. That's actually quite a nice effect. So that's using NeoPixel LED strips with a NodeMCU to create some pretty cool effects lighting with just a single strip of LEDs and one digital pin. There are some limitations with the software that we looked at in this video, but it has served me quite well. In a future video, we'll be taking a look at a better software project that is a lot more fully featured and removes the requirement for us to hard code things like the Wi-Fi SSID, the number of LEDs in the strip, and more. I do hope that this video has helped you in your smart home journey. And if there is a video that you'd like me to cover in the future, drop a comment down below. And if it's available in Australia and doesn't require me to sell a kidney to get my hands on it, I might just take a look and do a video on it. If you like this video, hit the thumbs up. And if you haven't already, make sure to subscribe to the channel. When you do subscribe, be sure to hit the bell icon so that you get alerts when I release new videos. Lastly, if you enjoy what I'm doing here and you want to help support the channel, there is a Buy Me a Coffee link in the video description down below. Thank you very much for watching. I'm Stu from Hive Mind Automation, and I look forward to seeing you next time. Bye for now.